let me share my screen. Hey, how can I share a screen? So here's our original plan. So we would have IC on data analytics due on week 11, and a visualization method in civil engineering due on December 9th. So I'm actually thinking, instead of having both, you can pick one of them to write, and we can move the deadline to December the 9th. So let's say you still want to write something about the data analytics in civil engineering. You do not need to turn in that on November the 18th, but still December the 9th. If you decide to write something about visualization in civil engineering, once again, the deadline is December 9th. So I'm just going to create that one IC and use that to represent both ICs. Make sense? So once again, we made two changes. One change is, instead of writing both ICs, you just pick one to write. And the second change is, no matter what you pick, the deadline would be December the 9th. Okay? Any question, any objection from the class?
Thank you, Lisa.
No. Okay, no objection. All right, great. So now I'm going to turn this over to my PhD students, Judy and Tianyu. So Judy, it's your turn now.
Okay. Hello, I'm Judy. Can you hear me?
Yes. And by the way,
Okay.
Judy is just finished the second year of her PhD, and she has worked a lot in human robot collaboration research, and also brain function analysis, like FNIRS data. And she has been using a lot of deep learning methods in her research. Yeah, Judy.
Okay, let me share my screen first. Okay. Now can you see both the point web and the code, right? Okay. Let's start the point first. First, I will talking about the convolutional neural network. I think you guys will confuse. I know what's the neural. I know the network, but I don't know what the convolution is. So I will briefly introduce what's the convolution. For example, this is a visualization of CNN, which is a convolutional neural network, and that is used to classify the picture into a cluster, a different class. For example, we have this picture, and it's basically a cup, maybe it's a cup of coffee, and most of the pictures have 3 channels, means red, green, and blue, and this will give the picture the colors. And by this neural network, for one layer, the convolution layer, the maxpro layers, then at the end they will output the features, and then they will decide, oh, by this feature content, we know this is espresso. It's a cup of coffee. So I think the first we need to learn what is a convolution. The convolution is this one. We have the pictures, and we have the kernel, and we have the output. Then how can we get these pictures into these pictures? We need to do a convolution process, which means this convolution will have 3 plus minus 3 multiple 3 kernel. And for example, you can see this is a bigger here, bigger container here, and this is just one container here. And the convolution is that we get the features from this 9 cubes, and by some functions, then we get the value into this picture. By this process, we can both get features and reduce the parameter we get. So
can I add something here, Judy?
Okay. Yeah.
Yeah. So basically, you guys remember that the way we represent the pictures are using numbers. So you can imagine 0 to 255 for each pixel. That's how we show a picture. And the convolution is actually a matrix calculation. You use you have a big matrix now here, and you times that multiplies with another matrix. This process is called a convolution calculation in matrix. By doing that, you receive a new matrix. And like Judy said, the reason we are doing that is we want to highlight some features in our original picture, that hidden features, by doing some kind of convolution calculation. And meanwhile, we can reduce the dimensionality by doing that. As you know, like Judy mentioned, originally it's a 64-64 matrix. Now it's reduced to 62-62. So
Yeah.
Judy and you'll be talking about, we have further way to reduce that. But a quick question, a quick comment here. Why we are multiplying that with this matrix? The answer is we don't know. This is still, something we don't understand, but it's working. People trying different matrix to do the multiplication convolution. Some are working better than others, and that's how it looks like. Yeah, Judy, you can continue.
Okay. And next, understand what is convolutional, and we will start with our journal from the coding. And I think after this class, we can basically understand this picture, because this picture is mostly used for describe how this LSTM model is. For example, we should know why this is a cube, and the cube is become smaller and depth and more deeper at the end, and why they are just become a line at the end, and this line can reflect our class, and we can basically on this line, and we can know what the picture is. So I also want to you have a basic idea about what is a tensor, what is a layer, what is the activation functions and loss functions, and optimizer after learning this class. And first, if we want to start a convolutional neural network in our computer, we maybe need this tool. The first tool is the editor, which we need to. I usually use the called the Visual Studio VS Code, which is very simple. And the second is Jupyter Notebook. It's more like it will help you to visualize and to debug your coding. And the most important is we use a programming language, and Python is widely used for machine learning. And also we need some tools to help us to deal with the mathematical problems, because we don't want to calculate them by ourselves. So this is the TensorFlow and the Keras. This is a very powerful tools for us to build our own neural network models. And all this can download free from the internet. And the first question is, because the TensorFlow is very popular nowadays, what is a tensor? And many neural network also use tensor in their articles. And I will basically introduce what a tensor is. Tensor, and don't let tensor scare you, because it's just a simple mathematical concept. It's more like a container, which we can use it to save our data inside the code. And why most machine learning algorithms rely on vector and matrix, but the deep learning will rely on the tensor, because for deep learnings we usually involve hundreds and thousands of dimensional fields, and we need to use more complex containers to save our data. And this is the difference from the tensor or similarity from tensor another container. For example, if we just have 1, 2, 3, we can call it a scalar. And if we have one dimension, it's called a vector. And we have 2 dimensions, a matrix. And if we have more dimensions, it's called a tensor. And this is a rank 3 tensor, which means the rank means the number of dimension, and the shape is the number of rows and columns, just like this one. And the type is which data inside this tensor. And so we also I can use more example to describe what the tensor is. For example, the image and the video. It's quite common in our real life. They can install into the 2D, 3D, 4D, and 5D tensors. For example, this is colorful pictures. Actually, it's a 3D tensors because here we have the height, we have the weight, and we also they have the 3-dimensional colors. And if we have just the grayscale images, they actually just have the two dimension. And this is 3D color image like this. We have raw colors channels, and this is 3D tensor. And if we have 3D grayscale image, which means we also have the depth information. So it's not just the a shape, it's like a plane. So we have plane, raw colors, and it's just also because it's grayscale, so it's also the 3D tensor. But if we add the color information, it will become 4D. And for video, because we add the time dimension, so they will have additional dimensions than just the pictures. Yes. Also, from the I have the for this one, we can see we actually have more very large dimensions, but actually in our idea or our conceptions, we just have for example color red, green, and red, this dimension. How can we add the dimension to pictures? This we call some concept called the filter, because for some computer vision, a picture can combination of more dimension, more than simply red, green, and blue. This color, they have some filter like this one. Actually, if we to use the computer vision to see the pictures, the basic unit of this picture could be something like this one. So we have multiple dimensions inside the picture. And also, as I mentioned before, we have different layers because we have basic container tensors. Then we need to add the layers to build up our neural network models. Like this one, we have different layers, and what the layers do is we do the convolution layers and the maxport layers, and all this we want to do is to extract the features and reduce the dimensions. And for example, this is a convolution layers, and we know what it do before, and we also have the maxport layers, which means it's a little simple than convolution layers. But for example, if we have the kernel like have 4, 2 multiply 2, and then we can just simply to calculate the max value of this 4 and get that value into our output. So it's simply like a blur effect. For example, we have the 16 multiple 16, but the output is 13 multiple 13. What's the difference from these two? I think the idea is both of them is help us to get some feature and to reduce the dimension, but this is more complex and this is more efficiency. And for machine learning, most of us need to consider is the balance between the accuracy and the computer efficiency. So we need the both convolutional layers and the maxport layers here.
Yeah, can I add something here?
Okay, yeah.
Yeah, you can see the filter here, and the filter, you probably question how do we visualize a convolutional matrix? It's actually a way to highlight certain angles of your original picture or certain color of your original picture. For example, in the left-hand side, it shows that a 45-degree line we can definitely then use a matrix to show what a 45-degree line means, right? So basically, you probably have a bigger number across the diagonal of that matrix. Make sense? And then you run the convolutional calculation, apply that to the original picture. You see the result basically highlights a lot of 45-degree lines. So like Judy said, the convolution, yes, it reduces the dimensionality, but it's more of highlighting the features in the raw original picture. And then the max pooling, like Judy said, is, we just use the biggest number to represent the 4 pixels. So we can just reduce dimensionality very fast. So then the max pooling is more about reducing dimensionality. So we are doing the 2 things, highlighting the features, which called feature extraction, and reducing the dimensionality. Yeah.
Mm-hmm. Yeah. Mm-hmm. Then we know basically the idea how this picture converts to this picture, but how it works, we need another called the activation functions, which means like the neural. We need to know which information need to convert to next layers or next neural, and this is it works by the activation functions. For these functions, we can choose the most valuable information and convert them to next step, and to reduce some boring or unnecessary information. Most popular activation functions is something it's a ReLU and the leak ReLU. For example, for these functions, we only consider about some values bigger than 0, and if the information less than 0, we just give them 0, so they will not convert to transfer to next neural, and we just transfer them the most important information. And
Can I add nothing here? You guys remember we talked about artificial neural network, and it's kind of like you as the neuron is receiving a lot of signals from your neighboring neurons, and you add them together, but you want to see if you decide to pass it on to the next neuron or not, depending on if it's interesting enough. So let's say if my job is to classify or to tell if the image is a building or not. Now imagine the building will have a lot of 90-degree lines and 0-degree lines, a lot of vertical lines and horizontal lines. So if I'm the neuron doing that kind of classification, if I receive a lot of curved lines, it's not interesting to me at all. So then I compare it with some established ReLU function, I probably wouldn't pass it to the next neuron. But if, I saw, in the filter, you see that I apply those things. If I see, wow, in this figure, after the convolution calculation, I see a lot of vertical lines. Yeah, it's so interesting, might be relevant to a high-res building. So then I probably pass it to the next neuron. That's what happens at a macro level.
Mm-hmm. Okay. So as shown above, we have built our neural network and we know how it works, and we also need to know what is right and what is wrong. So we need the loss functions and optimize functions. The loss functions means we have predict this picture is a cup of tea, but I needed to tell the model whether it's wrong or right. So that is the loss function do. They will judge whether the prediction value is right or wrong. But if we know it's wrong, how can we to tell the model, and how can we improve the model to according our results? So we also need the optimizer, which means if we know this feature to inflect this prediction is wrong, we need to adjust this parameter. So we need the optimizer functions to do this one. For example, for most functions, we need to because the bigger loss function means the model is prefer to run, but the less loss functions means the model is more accuracy. So we need to minimize the loss functions. And how can we find the minimized values? We also do the gradients, the gradients, and this gradients, the function is to try to find the best the loss values is optimized, is what the optimized function do. So
let me give a quick
yeah,
example of the
yeah.
gradient function, guys. So
Mm.
basically, like Judy said, the loss is bigger or small, then I try. So let's say I have this particular parameter and I change the value. So let's say the two direction, I can change it to make it bigger or to make it smaller. So I make it bigger. Oh, after I make it bigger, the loss is bigger. So which means, oh, probably I shouldn't go this way. Let me try the other way. I make it smaller. Oh yeah, after I make it small, this particular parameter, I make the value smaller, then the loss is shrinking. So I know, okay, instead of this direction, I should move that direction. The real situation can be even more complex. It's not just one direction. So imagine you are blinded and you are trying to find a direction to move, and moving that direction, like changing the value of your parameters, the combination of parameters in certain direction, I can reduce the loss the maximum. And that's called a gradient, descent gradient. So it's kind of like I'm searching, I'm trying different direction until I find a direction. I go in that direction, I can significantly reduce the loss or the error. And so I just keep doing that. It's kind of like you are blinded, but you are touching the wall, trying to find the right way, go to the exit. That's called a gradient, or that's optimization process. It's actually, you are adjusting the values of the parameters.
Yeah. Then step, I will use some coding example to explain what the neural network actually do. And this is the coding by Python. And
Judy,
the step,
we cannot see
okay.
your, we can,
Okay.
oh yeah, now we can see it, yes.
Okay. The first step, of course, we need to import our tools. For example, we need to TensorFlow, and we also need some visualization tools in this, and we just to play. Okay, we import all the tools, and it could help us to save a lot of works. And the first, and then we need our data, because we need to tell our model to learn from our data. And this one, we can, for example, we have, because data, it need time to load the data. And actually for data pre-process, you need to do something like the normalize, standardize to help you data in a same standard. This will help your model to train more efficiency. And as we have already loaded our data, we can show what the data look like. And for this part is how is show the data. For example, in data we have animals, we have cars, and each data have a label. And this is so this we can teach our model what is the car should be look like, and what the frog should be like, what the bird should look like. And then we need to create our convolutional model. For example, this is because by the TensorFlow and the Keras, it's very easy for us to build our model. We don't need to calculate anything. We just to set the parameters. So what the parameter do and what's this? Because this code do, I will explain a little more. For example, we had the first with an initial model. The second is we need to add layers inside the model. The first layer is the convolutional model. The second layer is the max Pauling model, and the convolutional model again, the max Pauling, and the convolutional model again. This is the action functions. Because there are several activation functions, we just need to choose the best one or the two for our model. And the input shape is means what this can be, you can think of the tensor. For example, we have the picture have 3 pixel plus 3 pixel, and we have 3 dimension RGB values. And this is the input you need to get for your layers. For example, this one is the kernel size. It's just you have a better understanding. This is the size of this one. It's a kernel. So we have multiple of 3. We have, it's just exactly it's if we visualize this kernel, it's just look like this one.
Yeah, so it's a 3x3 matrix.
Yeah.
Yes.
And this is the dimension you want to your layer to calculating. And the max polling is also, this one is the kernel. It's the kernel size. For example, is if we can, oh, I think there's no here.
Yeah, it's a 2x2 matrix.
It's a 2x2 matrix. So once you set up, you also can get called a model summary. So you can see what exactly inside the model. Oh, because I didn't run this one.
Yeah. So what you are seeing here is just a script description of the architecture of the convolutional neural network.
Yeah. And this is the supposed output of each layer. For example, after we input the layer is three dimension, but after the first convolutional, because we set it to, it will become the size will reduce, but the dimension will increase from 3 to 32. And after the max polling, the size reduced again, but the dimension didn't reduce. And then we do the second convolutional, we can see the size reduce again, and the dimension will increase, which means the feature, we get more features. And the max polling will not change your feature numbers, but will actually change your size, the picture size. And at last, we have the very smaller size of our feature matrix.
Yeah, so basically it means the pictures, the original picture becomes 4 pixel by 4 pixel chunks of things. You know, we cannot tell what they are, but they're 4 by 4 now.
Yeah. And they have 64 features for each pixel. And this is what don't have this one from this one. We actually have something look like this. Then after, we also have at the end, we need to do the flatten and the dense actions, which this means we can, from these pictures, we have changed the shape of by our layer convolution and the point layers, because, for example, the size becomes smaller, but the dimension become larger. We need to convert these features into actually feature size. That is called, it's for like you will broke the cube and to flat the cube into a vector, and this vector will decide which this original picture is. This is called the flatten functions. For this one, the flattened layers converts 3-dimensional layers in the network into 1-dimensional vector to fit the input of 4 fully connected layers for the classification. Actually, the last step is we need to get the information from the neural network and into our classifier.
The classifier itself is an artificial neural network. And since that artificial neural network can only see data in the vector mode, so the final flatten function is to, to convert the cube in line them up and to become like an arrow for the artificial neural network.
Yeah. And for example, well, after the flatten functions, actually the high dimensional information just flatten into the 10 features. And so we have a model, we have data, and then the next step we need to feed the model with our data, and this is called the training. And we need to first we need to this is a training process. But we can see, oh, seems my computer. Hello. Seems my computer blocked.
Yeah, we can hear you, I guess, but the demo computer is frozen.
Yeah.
Yeah,
Okay.
I guess Zoom actually consumes a lot of computing resource from a computer, and you are also running this training. But
Okay.
here the basically the epoch means how many iterations of training that Judy is running. It shows that this model just first randomize a lot of parameters and get a generated result and compare with the ground truths. It's kind of like somebody telling you, no, you are doing wrong. No, yes, you are doing right. And just repeat, and adjust the values for more than 1,000 times until they can generate a very close, the prediction very close to the ground truths.
I think I need to restart my computer. I'm
Sure.
sorry, so I need to.
Oh,
Yeah,
it's
okay.
fine. That actually, this is amazing. I think this is a very comprehensive introduction to CNN, but basic convolutional network. So basically, what you are doing, what you are trying to do, Judy, is to train the model and show how it can classify like a new picture, right?
Yeah.
Okay. Yeah, I think we got the point. So while you're rebooting your computer, maybe we can ask Tianyu to talk about RNN a little bit, and we can come back to you for the GAN.
Okay.
This
Okay.
one. Is that okay? Okay.
Yeah.
Tianyu, are you there?
Yeah, I am here.
Okay. Yeah, you can share your screen now.
Okay. Hi, can I see my screen? Yeah.
Yes, we can.
Yeah. Hi everyone. I'm a PhD student of Dr. Du, and I'm very grateful to Dr. Du for giving me this opportunity to share some of my view of LSTM network. And today I'd like to talk about long short-term memory, and instead of discussing some deeper issues such as network construction, the main purpose of my presentation is to give everyone a general understanding of the LSTM method, because there are many people have implemented this method, and there are many packages on the internet that can be used directly. So I just want everyone to know this method, and when you try to solve some problems, you can think, oh, maybe you can use this method. So this presentation is mainly divided to 5 parts. First, I'd like to make a short instruction of the neural network, because this is the basis of LSTM. And after introducing about the neural network, I want to talk about a special neural network, the recurrent neural network. And LSTM is actually an improvement version of the RNN. And then I want to talk about why LSTM appears. That is, what is the shortcoming of the standard RNN. Then we will focus on LSTM. And last, since there are already many mature LSTM network that can be used, so I want to talk about what kind of problem LSTM can serve. So maybe let's talk about the introduction of the neural network first. First of all, what is the neural network? It's called the neural network because it simulates the process that our brain deal with the signal and obtain a high-level result. Our body, the human body, can be imagined as a composed of many neurons. For example, our eyes and the sense of touch of our hand can be imagined as a neuron that are in contact with the outside world. And when these neurons are stimulated, they will generate electrical signals that transmit to another neurons. And this electrical signal can transmit through neurons to neurons, and finally form a result in our brain, such as the image, and can be seeing our eyes and the sense of touch of our hands. So, for example, for this simple neural networks, you can think of each circle as a neuron, and each neuron has its input and output, and each neuron can transmit the signal to another neuron, and finally, some neuron in the output layer can form a result. Then, the design of the neuron also comes from the brain. Like each neuron can receive an electrical signal from many other neurons, but some signals are very important and some may be not so important. So there is a weight between each neurons. The important signals has a larger weight, and the unimportant signal have a smaller weight. And each neuron performs a summation based on the received signal and the weight. But each neuron is not a linear function. It does not sum up all the signals and output it. It is similar to a binary active state, and there is an activation function, just like Judy said, such as sigmod, tangent edge, and ReLU activation function. And only when the total electrical signal reaches to a certain amount, this neuron will be simulated and send out an electrical signal. So what is the deep neural network? When the machine learning method began to develop, the performance of the computer was not good. So the number of layers in neurons and the number of the neurons in the neural network was small. For example, there may be just only one input layer, one hidden layer, and one output layer. And so people thought that the machine learning method was not useful because the ability for the simple neural network to solve the problem is weak. However, in recent years, with the improvement of the computer capability, people find out that the computer can afford the calculation for more neurons and more layers. And so neural network become feasible and popular, so people try to use it. And for the deep neural network, it's like there is a lot of layer, a lot of hidden layer. There is so much hidden layer, so it's become deep. So people call it deep neural network.
So guys now know what is deep learning. Deep learning is actually just really deep neural network.
Yeah, and then the computation complexity with this deep neural network is increased, but the ability to solve the problem also becomes stronger. So, and DNN is good at modeling the mapping from a single input to output, but it is not good at processing the sequence data, like time series data, such as sentence, sounds, and video. If you still want to process the time series data based on DNN, the DNN will make each input predicted separately and then aggregate the output together. So the result of this method is not good. So from my understanding, DNN does not consider about the sequence and the contextuality.
So what Tianyu says here is, if you have this DNN or deep neural network, and you tell it that this image is a cat, this is a dog, they can do this classification or image detection thing very easily for you. But if you ask the DNN model to predict the trajectory of a person moving, or if how the stock market price is changing, since it happens like recursively, and DNN is not good at that, and that's what the RNN, the recurrent neural network, comes in.
Yes. Yeah. So if we want to predict like a sequence data, we need to use recurrent neural network, RNN. RNN is a network specially used to process sequence data proposed based on DNN. We can say that there is a loop is unique to RNN and is called hidden state. The right side image can show the RNN network more clearly. What this image means is that the output of the time t or time one, and let's say time one, is not only output as a result, but also is an input of the time two. So that is for the RNN.
Yeah, so it's recurrent because output becomes input and then becomes input. So this repeat itself all the time.
Yes. So let's compare DNN and RNN. The calculation for DNN is a weighted summation of the input of each neuron, and then use the activation function to get output. But for RNN, the input is not only XT, the signal from other neurons, but also use the output of the previous RNN as an input. RNN can also go deeper, not only in the time sequence, but also in network structure. For example, in this paper, they not only deep in the time sequence data, but only in the structure, which means for each point of time, they use a lot of RNN to calculate the result. So RNN can deal with the time series data for a good result. It seems like RNN meet our requirement for sequence data, but it still has its shortcoming. Let's see. The first, sometimes we only need to look at the recent information to perform the present task. For example, consider a language model trying to predict the next word based on the previous word. The gaps between the relevant information and the place it needed is small. So RNN can learn how to predict this word. But there are also some cases where we need more context. For example, consider trying to predict one sentence and the dependent sentence is 2000 words before this sentence. RNN cannot predict it. So it is possible for the gap between the relevant information and the point where it's needed become very large. But unfortunately, as the gap grows bigger, RNN cannot predict the result very well. Another shortcoming is that RNN is hard to train. There's some problem like vanish and exploding gradient, which means the network is trained by gradient descent and the error backward propagated from the last time step to the beginning time step. So when the sequence is too large, the propagated error could be vanished to 0 or explode to NAN.
So basically what Tianyu says here is, remember the gradient descent is kind of like you're blinded and you're trying to find a direction to move. But when this RNN model becomes so big, you don't move at all. You're just stuck there.
Yeah. Just quickly introduce about the back propagation. And for my understanding is like we know the input and we know the output, but we don't know the weight in the neural network. And we want to know what kind of weights and can make this input to get this output. And so we first assume a set of weights as random and get the result from this input and compare the result we get to the original result. If these two results are different, we will use a backpropagation to adjust the weight. And after we adjust the weight for several times, the input data can get the result very similar to our original data.
Yeah, the BP, the backpropagation means, when we do the gradient descent method, we're not doing them all together. So basically we are moving them from the output layer to the most close hidden layer and all the way to the input layer. So it's kind of like a wave from the output to the beginning. We are doing them one by one, the gradient descent.
Yes. And I also want to simply talk about the gradient vanish problem. That is also one reason why RNN cannot remember a long-term dependency. For example, for neural network with 3 hidden layers, and when the gradient vanish problem occurs, the weight update of the hidden layer 3 close to the output is relatively normal, but the weight update previous hidden layer, like hidden layer 1, will become very slow, and causing the weight of the previous layer become almost unchanged, and the value of the hidden layer 1 is still close to the initial weights.
Yeah. So basically, all models are lazy. Like when they try to narrow down the gap between the predicted value and the actual value, they do the back propagation, but they figured out, oh, if I just do the most closed connections, it works. Why should I bother to go to the front end and do things? So the model becomes lazier and lazier, and it's very difficult to find the perfect combination of parameters that generate the best prediction.
Yes. So to solve this problem, so we need to use the LSTM, the long short-term memory. So we know that the advantage of LSTM is that it can remember the features for a long time. So compare the RN to LSTM. The repeated model in standard RN contains a single layer, but the repeating module in an LSTM contains 4 interaction layers. So the core idea for LSTM is that there is a cell state in LSTM that just straight down to the entire claim, and with only some minor linear interaction that can influence it. And for the let me talk separately about this 4 layers. First, in order to remember a long-term dependency, LSTM will repeat selectively forget some features. So the first step in our LSTM is to decide what information we are going to throw away from the previous cell state. And this decision is made by a sigmoid layer. This is a sigmoid layer, then called forget gate layer. And the input is the ht-1 and the xt. And the output of the sigmoid activity function is between 0 and 1. If the number is 1, it means we completely keep this information. And while the number is 0, it means we completely throw away this information. And the next step is to decide what new information we are going to collect in to the cell state, which called input gate layer. There has 2 parts. First, there is a sigmoid layer that decide which value we will update, and there is a tangent edge layer that create a vector of new candidates value that also could be added to the state. And then we will need to update the information to the new cell state, say CT-1. And while we added this information to the old cell state, we will create a new cell state that's CT. And this previous step have already decided by these two layers. And we will multiply the FT, and to forgetting the things we decide to forget earlier. And then we will add this new features to the state, and the new cell state will create. And then finally, we will decide to what we are going to output. And it should be known that the output HT is different than the cell state CT. So that is the reason why that is the reason why here the LSTM can keep this the long-term information for a long time.
So Tianyu, can you move a little bit faster since
Okay.
this is very detailed. But basically, what Tianyu discussed here is LSTM creates a backdoor for some earlier information to sneak into your current module. So it actually opens a backdoor for that.
Yes. Okay. And so for my understanding, that LSTM has a self-measurement standard, and it will selectively forget some unimportant features and remember more important features. And also the layers in LSTM can be changed and optimized, like the Peephole connections, and there is a gate recurrent union. This one is pretty new and is very famous now, and it says that it have better performance on a certain small and less frequent data set.
So basically, what my understanding is, you have a lot of gatekeepers. It's kind of like you're going to like some game, going through the stadium gates, and they have different designs of standard to let you in or out. And so they have different ways of keeping or forgetting the older information. But why this model is better than others, once again, we don't know. That's the magic part of a neural network of deep learning. Sometimes it's working, and we don't quite understand why.
Yeah, and finally, I want to talk about some what's the problem LSTM can serve. Yeah, and if we have a problem, and construction neural network will LSTM node is flexible and should fit our problems. For example, there is some one-to-many, and many-to-one, and many-to-many. And for example, to one-to-many, it's like the input is not sequenced and the output is sequenced. This example is that we give the model an image, and the model will give a result like how to describe this image. However, there's still some errors like here, but for most of the images, their describe is very accuracy. And also for many-to-one, such like the video classification, and they have a video and they use CNN, just Judy introduced, and they use like LSTM and you classify the videos.
Yeah, so the one-to-many means you give them a static image and it basically predicts what will be going on in terms of the moving of the objects in the picture and try to infer what that is. And this many-to-one is to give them a stream of video, which means potentially like a whole lot of pictures, and run Judy CNN to classify each of the frame. And then based on all the frames, the description, I know, okay, this is probably means somebody is playing tennis ball. That's the many-to-one.
Yeah, and for many-to-many, I'd like to talk about our experiment. What I'm doing now is I try to use the human eye tracking data to predict the hand movement data. So first, let me just briefly introduce our experiment procedure. In our experiment, and the participants need to remember the sequence of turning the walls and the position of the walls, and then they need to remember the sequence and follow the instruction to complete the environment. Like in this image, the participant wear a VR device with a built-in eye tracker, which will record the participant's eye tracking data. The eye tracking data is just like the special point, position of the gaze point.
So can we jump to the LSTM part and not talking too much? I just basically what we are doing here is we collected the eye tracking data and also the hand motion data from 120 people. And we do have assumption like where you move your hand depends on where you look at, right? That's usual what happens, right? So yeah. Tianyu collected 2 time series data, and his goal is to, if we just have a person's eye data, for example, I'm looking at the door, how I'm going to move my hand, right? So we want to predict that, so we know in the future, you know, if there's a robot working with me, we can avoid potential injuries from the robot. Yes, Timmy, can you actually jump to the result part? We still have Judy's stuff.
Oh yeah, okay. And we try to use our eye tracking data to predict the hand movement data, and we use LSTM to train the model. And this is the prediction result for my experiment. Here, the orange line is the original data of the hand movement, and the blue line is the predict result for the hand movement data. And this is the prediction result in X, Y, and Z. And although there are 2 lines, the 2 lines maybe sometimes they are not fit very well, but the overall trend of these 2 lines is very similar. So we can briefly introduce what people's hands want to move to which position or which direction. So that is the effect of LSTM prediction. That's all. Thank you.
Thank you, Tianyu. That's amazing. And I guess now you guys have a general understanding what LSTM. It's just a recursive neural network to predict time series data. And Tianyu's research actually focuses on, you know, can we use one time series data to predict another? Or it can also be, you know, the same time series data to predict the future trend of that, such as if a person is driving a car. And so Tianyu's model can predict where the car is moving. And this is perfect for autonomous vehicle. That's the application of LSTM, right? All right, thank you again, Tianyu. I think that's really, really comprehensive. Thank you. And Judy, are you back?
Okay.
Yeah.
Can you see me now? See the screen?
Not yet. I think it's still loading. Yes, now we can see it. Yeah.
Okay. Just a summary of the CNN. Come back to the convolutional network. In my understanding, I think CNN is the process. You can represent you can use a very smaller picture to represent the big picture. Why it works? Because each unit of the smaller picture contains more information, more high, because we can see the dimension of each unit is increasing, and so even the picture is become smaller, but each data contain more information and more features, and that features values for classification. So the next step, I want to introduce something is improved by the is called the generative adversarial network, which is called the GAN. What is the GAN? Because from CNN, we have understand that we can represent a picture by a lot of features. And because we understand these features, can we use these features to generalize a new pictures? For example, if we know a cup will have water, will have white colors, can we use these features to generate some nano colors? So this is the gun do. For example, they have the generator and the discriminator. Discriminator is basically what the CNNs do, but the generator is just the inversive operations of the of a CNN. For example, we have a lot cat images, and we know the cat images should have some features. For example, the round eyes, the shape the shape ears, and the color of their skins, and we tell we have tried, and our generator will try. Is that one is right, and then this result will into the discriminator, which is the CNN model. And after several steps, the generator will generate very true pictures like a real cat. This is also some jokes like for the guns. For example, we have some people want to draw pictures from like this one, and the teacher, the discriminator, like the teacher will tell, oh, it's wrong. The fish should have some other features. And what can we do? And this is a more explain. This is the architecture of the gun. For this part, it's the discriminator. We can say it's very similar from the CNN. Actually, it's just a CNN architecture, and this will decide which picture is real and which picture is fake, and they will tell the generator to draw better pictures. For example.
Yeah, sorry, Judy, can I add something here? And this is a perfect slide to stay. Basically a big problem for a lot of machine learning, including CNN, is the lack of training data. Because machine learning is a monster, it needs a lot of data. So in 2017, a genius, it's a PhD student at that time from, I think it's University of Toronto or some university, I forgot. He had this idea, can we train a machine learning model to cheat another machine learning model and ask them to fight each other? So basically the generator is something that is generating fake pictures. And then the discriminator is trying to tell if it's fake or not. So they are fighting each other, and they are becoming, they are becoming better at the same time. So the discriminator will say, oh, this is definitely fake because of this and this and this. And the generator say, oh, that's how you discover this is a fake picture. Let me improve that. And then discriminator say, wow, this is better. How did you do that? The generator say, because I did this. So they are doing the two things, and you can see from the architecture, the opposite things. And it's kind of like they're playing their internal game without additional data. They are generating fake data and much, much better data. This is a genius idea invented only about 3-4 years ago and now become so popular.
Okay. And we can see they just this architecture just is the inverse model of the CNN. So they are just some inverse operations. For example, we have a convolutional in a CNN model, and we have the inverse option called the transposed convolutional functions, layers. You can just imagine this is just the inverse of the functions we use in CNN. And then we have the max polling in CNN, and we have up sampling in a generator, which means we will increase the size and the data in the generator. So they are just the inverse operations into these two models. And what's the gun can do? And I have this is some examples. These examples, we have the picture like this, and we have pose like this, and we give this to our gun models. They will generate some people like this one, because they have the pose, they have similar the appearance like this girls, but they have a different pose. And this is also some other examples. We have the condition images, and when we have the target pose, and at the end they will generate some people in different pose. but with very similar appearance. That's what the GAN can do. They can generate some very similar images what you want them to do. And this is the architecture. And this is another use, because for face recognition, we also need to some very detail of one's face, but actually in most cases we just have part of this one's face, but by GAN we can generate what the people look like in different angles. For example, because we have the so we know which features can represent these people. So we get these pictures, and these pictures and use these pictures to tell our generator the people should have this this kind of mouth, this kind of nose. Then the generator will learn, and they will these people. Even though we don't know they are in front should look like, but we know his eyes look like, his nose look like. We can generate the face, the front face like this. This is what the generator can do, the GAN can do. And I will simply show the coding for this. I will use the very simple symbol used to recognize the written letters. How the GAN can generate the letters to by itself. The first step is also we can.
Judy, you mean the handwriting letters, right?
Yeah,
to mimic how a person would write letters.
Yeah. And the first step also we need to import some tools, and this is our data, so we can show the data like we can. Okay, yes. Because I'm afraid to it's broken again, so I will just wait a minute. It's our previous result. If it doesn't work, we can also show this previous result. Okay. And we load the data, and this is how the data look like. For example, we have tried different. This is the handwriting data, and this data
so these are the real handwriting data from real people, right?
Yeah. And we also need to do some training to normalization part. This one. And after that, we need to feed our data into our batches, because for our GAN's model is more complex. We need to do some process about this one. Okay, for this one. And the next step, we need to create the model. For example, this is make the generate model. We can see we have much similar layers like CNN, but just the inverse operations. For CNN, at the end we will do the dance, do the normalization. But at first we should do this one. Then we need to add the layers for example, for CNN, we have to do convolutional layers. But in this model, we need to add the this one called is transported convolutional layers, and another layers called the upsampling layers. But in this model, we didn't add the upsampling layers. We just to add some convolutional transported convolutional layers, and and also to add some activation functions to make its information transferring. So let's see what's at the beginning, what's the generated result. The output, this picture is the picture the generating without any training. So we can basically say it's just a very, very noisy. So we need to our discriminator to tell our generators which we should to save and which we should to throw out. And this is a generators. Oh, because I didn't. And this is the generator's summary. And then we need to define our discriminators. Actually, the discriminator summary is exactly the same model. For example, we have convolutional layers. We have the activation functions. We have flatten functions. So what's the next step? The next step we need to define our loss function, and in this case we use the cross entropy as our loss function, and also we need to define our optimizer, and all these things will help us to training our data. Because I'm afraid I will this computer will broken again. So I just show some of the outputs, how I previous outputs, how it's generated the things. This is the result of our generator. We can see from very beginning, they're very noisy. Then after each training process, they will become very much similar to our input data. And this is totally the generating the handwriting data. And we can find the result, even though its result is not that good, but I think we can basically recognize the number here. But if we have some more detailed design, and we can do something like this, we can generate very complex pictures, and we can fill them with very detailed information. And this is what the GAN actually can do.
Thank you so much, Judy.
Mm-hmm.
So let me show you guys something. I just when Judy was presenting this one, but by the way, are you done, Judy?
Yeah.
Okay. Yeah. So when Judy was presenting this one, I just searched quickly who invented this GAN method. It's actually Ian Goodfellow in 2014, so 6 years ago. While he was a PhD student at the University of Montreal, now he's working for Apple. So originally his thought was to solve the small data size problem for the discriminator. So he wants to train better classification model. Without enough training data, the model can also learn things. But unfortunately, humans are so evil, and they just figure out the byproduct of this method is the generator. You guys make sense? So I originally thought, oh, I just want to train better classifier, but no, it's more interesting to have a generator that can fake things up, like a generate things. So I want to show you guys quickly a website. You can go there. It's called "This Person Does Not Exist." Every time when you refresh this website, the generator generates a fake person that does not exist in the world. It's just the computer, the machine learning model learns from the features of person and just randomly generate a face for you. And this person just does not, these people just does not exist. You can tell from for details, some place looks weird a little bit. Different races, different ages, different gender. These are all fake pictures. Imagine how scary it is, and also fake videos potentially. And also, if you check Nevada, they have this product based on GAN that if you do not know how to, they can generate the fake pictures. So let me show you this video quickly.
Try and darken that up a bit with some cloud. Oh, that's wonderful. What if we were to change all that to rock?
Okay, let's click on rock, and we gotta replace the mountain.
Let's try waterfall just by pulling water down from the top there.
Okay.
Wouldn't it be great if everybody could be an artist? If we could take our ideas and turn them into compelling images? This technology allows us to create a smart paintbrush so that if you wanted to create a new picture, you can just draw the shapes of the objects that you want, and the neural network can then fill in all the details. If we add a water feature, the network is able to add reflections, not because we told it that, but because it learned it. Or if we change the ground to be covered in snow, then it knows that the sky also needs to be a different color. I really think this technology is going to be great for architects, designers, people making virtual worlds to train robots and self-driving cars. The input to this model is something we call a segmentation map. It's like a coloring book picture that describes here's where a tree is, here's where the sky is, here's where the ground is, and it doesn't have any details. And then the neural network is able to fill in all of the texture and shadows and the colors based on things that it's learned from a large database of real-world images.
I would like to see that tree reflecting in that pond.
The real advance here is that we're able to synthesize images with a lot more diversity and more fidelity than we were able to in the past. I really think this technology is going to be great for the dreamers of the world.
Okay, how do you guys feel? First of all, thank you so much, Judy and Tianyu, for giving us such a comprehensive and a detailed, presentations on your work. And as you guys can see, they are also PhD students in civil engineering, so you would never know how, deep learning and machine learning can benefit civil engineering. Like Judy's research is about check the neural functions of a person operating a remote robot. And so her works involve a lot of can I predict this person's status, based on the data I have. And Tianyu's research, like I mentioned earlier, is talking about when construction robots and a person working in the same place, and how the construction robots predict a person's motion and then try to avoid any spatial conflicts. That's all deep learning involved. And so what do you guys think? You guys see all the works, all the works they have done, and also people are using. And I hope you guys can also feel that they are all based on the general principles of, moving from this parametric to non-parametric. So you're moving from a more white box type of knowledge to a more black box. Like I mentioned earlier, the most scary thing about deep learning is they are working, but we don't know why they are working. And it's still a very hard question to answer today. It just, I think we are opening the Pandora's box now, and I don't know. Think about that. They create fake faces, they create fake pictures. We are getting the ability of God. We are creating things, right? That's AI. So what do you guys think? Nothing. If you guys don't have any question, I think Judy and Tianyu would feel side, after such a great presentation. Come on, just maybe quick comments or quick questions for them before they leave. No? All right. Okay. Thank you, Judy and Tianyu. And also, like I said, I'm going to send an email with to you guys to update the new deadline for the essays to confirm that. And next week we will keep talking this data analytics. Originally, I was thinking to start with some simple methods, but since given the schedule for Judy and Tianyu, so we just covered this machine learning first. But the next week we will finish up the machine learning. So we will be talking about some other methods such as sparse coding. And then we will move to like a simpler method, like the traditional statistical analysis. This part of the data analytics. And then a pre-warning, the final exam, I will give you some simple data analytics questions. So you will somehow know how to use the software package to do that. All right. Thank you guys. And without further questions, comments, see you guys next week.
Thank you, Professor.
Bye.